finite. Okay, the next example is called the piecewise defined function. This function have three parts or three pieces. Each part or each piece is defined differently. So in the first piece, fx is defined as 2x. And that piece is for x less than -2. So in the graph, you can see on the left part, there is a line with slope 2, right? Fx equal to 2x. So that's a straight line with slope 2. But it is a piece up to -2 for x, not including -2. So we got open circle in here. If you look at the left piece, and then we have the piece in the middle, fx defined as x squared. So that's part of the parabola, and this piece is valid for x greater than negative or equal to -2 and less than 1. So you can see the graph. We got a part of the parabola, and the left-hand point of the parabola is at the x equal to -2, including -2. So we got the closed circle on the left, but on the right side we got the open circle on the parabola at x equal to 1, because 1 is not included. X equal to 1 is not included in this part, in this piece. And in the third piece, we got fx equal to 4 minus x. Again, that's another straight line with slope -1. You can see it. And that's valid for x greater than or equal to 1. So again, the left-hand point, the x equal to 1 is included in this piece. So we got the closed circle on the left of this piece of line. All right. So that is still a function. Remember, you can check for any specific value of x you plug into the function, you only get one value of y or f. So that is a function. For example, what's the value of f of -3? So we need to value the function at x equal to -3. And if you check the formulas in these three pieces, that will fit in the first formula, because the first formula fx equal to 2x is valid for x less than -2, and -3 is less than -2. So we use the first formula to evaluate the function value at x equal to -3. So that's 2 times x, 2 times -3, that's -6. Okay. How about the f of -1? So this time x equal to -1, then obviously that will fit in the second formula or second piece, because -1 is between -2 and 1, right? So that's why we should use x squared. So we got -1 squared, which is 1. How about f of 4? So this time we're going to use the third piece of third formula, because 4 is greater than 1, okay, or greater than equal to 1. So that fits the third piece there. So we should use the third formula. So 4 minus x, which is 4 minus 4 equal to 0. All right, so that's how you evaluate piecewise defined functions. That's very tricky times, okay? The next thing is called, identify functions. Let's just use the definition of functions to identify some functions, whether there are functions or not. So the first example is a set of ordered pairs, 2, 3, 4, 1, and 4, 5. So this relation is an ordered pair, a set of ordered pairs, but is it the function? No, it is not, because we have two different values in the second coordinate for the same number 4 in the first coordinate. namely we get 1 and 5, right? So this is not a function. Number 2 or B, 3x plus y equal to 1. Yes, because for each value of x, you can use this equation to solve for y, and you only get 1 value for y. All right, so this is the function, and we know that's a linear function actually. Negative 4x squared plus y squared equal to 9 in plus c. This is not a function again, because for each value of x, you plug in, you're going to get 2 values for y. When you take the square root, remember, you solve for y by taking the square root after you move in 4x squared to the right, okay? When you take a square root, you get the plus or minus for y. So there are 2 values for y for each value of x. So that's not a function, okay? And how about this graph? Okay, so this that's another representation of function. We want to know whether that's a function or not. Yes, it is a function because you have 2 sets x and y, and for each value of x, you only have 1 value. Okay, one second. Okay, you can only have 1 value for y corresponding to it. Okay, for each point in set x, there's only 1 arrow going out. So there's only 1 value in set y corresponding to it. So that is a function. Defines that defines a function. Okay. So any questions? I think you can speak now. I think I can hear you a little bit. At least some people already tried today, so you can try to speak with me instead of tapping. Yes. See, Rudolph, right?
Yeah,
So
yeah.
yeah, it's working
You
now.
get
So yeah, it's good. So we're good now. So we don't have any more problem with the audio like before, right? So I'm pretty glad. So we got that working. We have been bothered by this thing quite a bit for a long time. Okay, can I move to the next page? If we don't have any more questions, Rudolph?
Yeah, you can go ahead and move on.
All right, okay. Yeah, I thought that was you. Okay. So I'm going to the next page, all right? Okay, well, one of the important things about a function is to find the range of domain, okay? Some people still not quite clear what the domain means. When I ask a question about the domain of function, they always answer me, the x. That's not the wrong answer. You need to tell me specifically what the values of x in this specific function. Okay, like in the first example, g of t equals 1 with t minus 4. What are the values of t? So t is the independent variable here instead of x, by the way. So what exactly values of t that we can use in this function that makes sense for the function itself? And it turns out the only value we cannot plug in for t is t equal to 4. So all the values from real numbers can be plugged in the function for t except 4. So that's the domain. The domain of the function is all real numbers except 4. So if you use the interpretation, that will include all the negative numbers to 4 and from 4 to positive, and to 4 to all the positive numbers. So that just excludes the number 4 itself. This interpretation essentially just excludes the number 4 itself. All right. Okay, so that's the first example. The second example, we're talking about the square root function and square root x plus 1. So again, you want to find all the values of x in this specific function so that the function makes sense. Okay, so this function is a root function. We need to take the root of x plus 1. So we want to make sure we can get a real number when we take square root. And that means the number x plus 1 in the radical under the radical should be positive or 0. And that will pose a condition for the number of x that can take. It turns out the x has to be greater than or equal to -1 if you solve the inequality of x plus 1 greater than or equal to 0, which is required to take the square root. So that means the domain of this function is all the numbers greater than or equal to -1. If you write in the set notation, it'll be like that. Okay. So you have to look at the function itself and see what makes sense to the function itself, and that will give you the domain. Okay. In the third example, a of s equal to s squared. So this formula of the area of a square with a side length s. Okay. So you want to find the area of a square with side length, that's s squared. Okay, so for the function itself, you can plug in any value for s. So mathematically, it works for all real numbers, but in reality, since we are talking about the side length for a square, so it has to be positive. So in this real world problem, the domain of the function will be all positive numbers, or if you in write it in into notation, will be from 0 to infinity, not including 0 itself. Okay, let's see what you say. You can just talk with me. I think it is working out. Can I be excused? My lights went off throughout my whole dormant day. I can't charge my phone or computer. Okay, yes. Right. Okay, that's fine. If you got any problem with Sydney, if you got any problem with your power, you can view the videos later. Okay, I'm going to upload it in Blackboard as before, so no problem. Okay, any questions about domain? That's the important thing you want to know or want to learn. If there's no question, I'm going to move to the next page. Okay, how do you graph function? We know how to graph simple functions, but how do you graph piecewise defined function? That's a thing that a lot of people have some issues. Okay, when you try to graph a piecewise defined function, you have to draw the piece by piece because each piece has a different formula. So you have to do it piece by piece. So like in this example, n of x equal to 2 if x is less than or equal to 1, and n of x equal to x if x is greater than 1. So you're going to draw the two pieces. One piece is for x less than or equal to 1, and the other piece is for x greater than 1, right? So x less than or equal to 1 means the piece on the left of x equal to 1. And x greater than 1 means the piece on the right of x equal to 1. Okay, so the first piece, it says n of x equal to y, or n of x equal to 2, or y equal to 2. So the left piece will be a horizontal line at the head of 2. Remember, y equal to 2 is a horizontal line at y equal to 2. So that be horizontal line showing the graph up to x equal to 1, and x equal to 1 is included in the first piece. So we got the closed circle in there, or dot. And then we have the other piece on the right, valid for x greater than 1, or on the right of x equal to 1. And that's y equal to x, or n of x equal to x. So you got the line with slope 1. Well, this piece only valid for x greater than 1, so you got the open parentheses on the left end point at the x equal to 1. And the graph will be like this. Okay? So one way to draw piecewise defined functions is to draw each piece and then you just erase the part that does not belong to the piece. Okay.
Mr. Liu,
Yes.
did you say it was horizontal and straight because it has the equal to sign for
Yeah.
the
Yeah. And remember, n of x equal to 2 is the same as y equal to 2, and that's a horizontal line, right?
yes.
If you draw the horizontal line, draw the graph of y equal to 2, that's horizontal line. Any other questions? Okay, so that's this example. And there's one typical way to determine whether a relation is a function or not, or any curve you can determine whether it's a function or not. That's called the vertical line test. You just draw vertical lines and see how many points it intersects with the graph. On the left, we got the graph like this, and it intersects the curve. The vertical line intersects the curve at 3 points, right? So that's not a function. On the right hand side, we got the vertical line intersects with the curve at most 1 point. Okay, for any vertical line, it can only intersect the curve at most 1 point for a function, right? So, okay, this is some terminology here: increasing, decreasing, the constant function. Okay, that's easy to understand. In the graph, where you can see there are 3 pieces. The piece on the left is going down, so that's decreasing. And the piece in the middle is flat, that's constant. On the right, the curve goes up, so it's increasing. All right. Okay. So we're talking about the functions. We know we can use vertical line test to determine whether a relation or curve is a function or not. And then there's another thing we call the one-to-one functions. What it means by one-to-one function. Given any value of y of a function, there is only one value of x that can be paired with the y. Okay, so that's a different definition with function. That's called one-to-one function. So such a function is called one-to-one function. So one way to determine a one-to-one function is to draw a horizontal line. So that's called horizontal line test. If you have intersections of a horizontal line with the curve more than 1 point, then it's not a one-to-one function. Okay, so you can see on the left, this curve is a function. If you draw the vertical line, it intersects at most 1 point with the graph. But if you draw a horizontal line, you can have 3 intersections with the curve. So that's not one-to-one. For any y value, you have 3x value paired with it. So it's not one-to-one. On the right-hand side, we do have one-to-one function. If you draw horizontal lines, it intersects with the curve at the most 1 point for any horizontal line. Okay, so that is a one-to-one function. All right. Okay, next example is a little trickier. It's called greatest integer function or floor function. I don't know if you've heard about that or not. It is defined the greatest integer that is less than or equal to x. Okay, so this is like truncation, right? It's like a rounding off function. So when you know uh, in computers, when they have some decimals, they might truncate it like this. Okay, so it does make sense, this function. So this function is defined as the greatest integer that is less than or equal to x. Okay, so what does it mean by that? Okay, we're going to see some examples. The notation for this function, has different, ways, and there's some other ways too. You can also write the floor parentheses x. That's also the same thing. Let's see what it means. Okay. For example, if x is negative 1.1, so what's the function of this value? So we need to find the greatest integer that is less than or equal to x. So the greatest integer less than or equal to negative 1.1 is negative 2, isn't it? It's not negative 1 because negative 1 is greater than negative 1.1. So we need to find the greatest integer that is less than or equal to negative 1.1. It's not negative 3 because it's not the greatest integer that is less than or equal to negative 1.1. And the number we're trying to find is negative 2. That's the greatest integer less than or equal to negative 1.1. Does it make sense? What's the function value when x equal to negative 3? That's negative 3 itself because it is the greatest integer that is less than or equal to negative. So in this case, it's equal to negative 3. It is an integer. Then the greatest integer less than or equal to negative 3, right? What's the function value when x equal to 5 over 2? That would be 2 because 5 over 2 is 2.5, so you just get the integer very next to it, less than it or equal to it, and that's 2, right? What's the value of the function when x equal to 5? It is 5. And that's the nearest integer that's less than or equal to 5, right? Well, what's the function value when x equal to pi? So pi is 3.14 something. So you need to find the nearest integer that's less than or equal to 3.14, and that's 3. Okay, so that's this function. And you try to graph this function, it'll be like this. Sometimes it's called a step function. Okay, they have different names for this function. So you can see this function is like a step. You know, it get one value between any two integers. So for example, from 0 to 1, when x is greater than or equal to 0 and less than 1, the function value is equal to 0. When x is greater than 1, less than or equal to 2, the function value is 1. You can easily check that by using the condition or definition of the function. Okay, for example, when x is between 0 and 1, okay, greater than or equal to 0 and less than 1, then the nearest integer that is less than or equal to that will be 0. Okay, right? Like 0.3, and then the nearest integer that's less than or equal to 0.3 is 0. Or 0.7. When x equal to 0.7, then the nearest integer that's less than or equal to 0.7 will be 0. Okay, but when x is equal to 1, then the nearest integer less than or equal to 1 will be 1 itself. So in here, we got the open circle at on the x-axis. That means that point is not included. Instead, the function value is 1 when x equal to 1. So we got the closed circle, on the left of the uh, line segment at y equal to 1. All right. Uh, so that's why you got all the open circles on the right hand of each piece, but the closed circle on the left end of each piece. Okay. So that's called the floor function. Floor function greatest the integer function or section. Okay. All right. Let's do the example of application for functions. Okay. So in this example, we are trying to fold a square to make a box, open box. So an open box is to be made from a square piece of cardboard that measures 40 inches on each side. Initially, the whole piece of the foil, the square, has 40 inches for the side length. And then to construct the box squares that measure x inches on each side are cut from each corner of the cardboard as shown below. Okay, so you just cut off the 4 squares shaded in the graph in the figure. You cut off those 4 pieces at the corners with each piece uh, a square shape with the side length x, and then you just fold the remainder of each side up to make the open box, right? Does that make sense? Okay, so then we need to compute the volume of this box. So express the volume V of the box as function f. That's part A. B, determine the domain of this volume V of the box. And C, oh, that's not A, I'm sorry. The length of the box is, okay, they only have two problems. Okay, so we talk about the part A. So we need to find the volume of this box. Okay, so the formula for the volume of this box is just length times width times height. So we need to calculate each part and then just multiply them up. So the length first is 4 is 2x. So in the base we get we get square for the box, and the side length for this of the square is just 40 minus 2x. So you got the 40 originally, and you cut it, at each corner by a square of sine x. So you are left with 40 minus 2x, right? You cut 2x, one from left and one from right. So you just have 40 minus 2x after you cutting. And they're the same on each side. Okay, so that's the side ends in the basement in the base. So that's the length and the width of the box, and then the height, is just x because that's what you cut and then you fold. So what you fold is what the length you cut, the part you cut, you fold up this x. So the height is x. So the volume is 40 times 2x times 40 times 2x. That's the square on the base times the height x. So that's 42x squared times x. And then we need to define the domain, determine the domain of the volume of V. So basically, again, we have to consider this application problem. We know both the length, the width, and the and the height must be positive. Okay, when we talk about the box. So we got 40 minus 2x, which is the length or width uh, at the bottom or the base of the volume or the box. That be positive, must be positive. And the height, which is x, when you fold up, that's must be positive too. So you just solve these two inequalities. 40 minus 2x greater than equal to greater than 0. We did those kind of things before. So you move 40 to the right, you get negative 40. And then you divide by negative 2 sides, and you reverse the inequality. So you get x less than 20. Okay, negative 40 over negative 2 is positive 20. And then we got the x greater than 0 and the x less than 20. So the domain of this function, v, volume of the box, is greater than 0 and less than 20. Okay, so you cannot cut more than 20 feet, because you cut from both sides, right? And you have to cut something to make a box. So that's greater than 0, less than 20. So that's